In the context of performing available short-circuit or fault current studies on alternating current systems, the contribution of direct current motors is generally considered to be negligible and is typically not included in the calculations. The primary reason for this exclusion lies in the fundamental differences in the operating principles and characteristics of direct current and alternating current motors, particularly concerning their behavior during transient fault conditions. Alternating current motors, especially induction motors, play a significant role in contributing to fault currents due to their inherent ability to act as generators for a brief period immediately following a fault. This behavior stems from the motor's stored kinetic energy in its rotating mass and the presence of a magnetic field established in the stator windings. When a short circuit occurs in the alternating current system, the voltage at the motor terminals drops abruptly. This sudden voltage drop causes a reduction in the motor's back electromotive force, commonly referred to as back electromotive force. The back electromotive force normally opposes the flow of current through the motor windings. With the reduction of back electromotive force, the motor effectively becomes a generator, converting its stored kinetic energy into electrical energy that is then injected back into the alternating current system, thus contributing to the overall fault current. This contribution from alternating current motors is a critical consideration in short-circuit studies, as it can significantly increase the magnitude of the fault current, which directly impacts the selection and coordination of protective devices, such as circuit breakers and fuses. The magnitude of the contribution from alternating current motors depends on several factors, including the motor's size, its impedance, and its operating speed at the time of the fault. Larger motors and motors operating at higher speeds will generally contribute more fault current. The impedance of the motor windings also plays a crucial role, as lower impedance allows for a greater fault current contribution. Various standards and guidelines, such as those provided by the Institute of Electrical and Electronics Engineers, offer detailed methodologies for calculating the motor contribution from alternating current motors during short-circuit studies. These methodologies typically involve using equivalent circuit models of the motors and applying symmetrical component analysis to determine the fault current contribution under various fault scenarios, such as three-phase faults, line-to-line faults, and line-to-ground faults. Conversely, direct current motors do not exhibit the same fault current contribution characteristics as alternating current motors. Direct current motors operate on the principle of converting direct current electrical energy into mechanical energy, or vice versa, using a commutator and brushes to maintain a constant magnetic field orientation relative to the rotating armature. Unlike alternating current motors, direct current motors do not inherently possess the ability to act as generators and inject significant current back into the alternating current system during a fault. While a direct current motor connected to an alternating current system through a converter or rectifier may experience some transient effects during a fault, the contribution to the overall fault current is typically minimal. Firstly, direct current motors are often fed by direct current drives or power supplies that incorporate protective devices such as fuses or circuit breakers that quickly isolate the motor from the alternating current system in the event of a fault. These protective devices limit the duration and magnitude of any potential fault current contribution from the direct current motor. Secondly, the internal impedance of a direct current motor and its associated drive circuitry is generally high enough to significantly limit the fault current. The armature resistance and inductance of the direct current motor, along with the impedance of the direct current drive components, effectively dampen any fault current contribution. Thirdly, the control schemes used in direct current drives often include current-limiting features that actively restrict the motor current to safe levels during transient conditions. These current-limiting features prevent the direct current motor from contributing excessive fault current to the alternating current system. Fourthly, the connection of direct current motors to alternating current systems typically involves power electronic converters, such as rectifiers or inverters. These converters introduce additional impedance and control functions that further reduce the likelihood of significant fault current contribution from the direct current motor. In summary, The contribution of direct current motors to fault currents in alternating current systems is generally considered negligible due to several factors, including the presence of protective devices, the high impedance of direct current motor circuits, current limiting features in direct current drives, and the use of power electronic converters. Therefore, direct current motors are typically not included in the calculations for available short circuit or fault current studies of alternating current systems. The focus remains on the contribution from alternating current motors, synchronous generators, and the utility grid to accurately determine the fault current levels for proper protection system design and coordination. It is important to note that while the contribution from direct current motors is generally negligible, there may be specific scenarios or applications where a more detailed analysis is warranted. For example, in systems with very large direct current motors or specialized direct current drives, it may be prudent to evaluate the potential fault current contribution to ensure that the protection system is adequately designed. However, in most common industrial and commercial applications, the exclusion of direct current motors from short-circuit studies is a valid and widely accepted practice. The specific standards and guidelines used for short-circuit studies should always be consulted to determine the appropriate level of analysis and the factors that need to be considered for a given system.